Work. Yeah. All right, so we did kind of read through this one yesterday to start, but I'll just kind of start over again. This was the fourth question on the 2008 exam. It was no calculator. They gave you the velocity function. They told you that the velocity was 0 at 0, 3, and 5, so what appear to be x-intercepts or x-intercepts. It also told you that there were horizontal tangents at 1 and at 4, which we said yesterday means that the what is equal to 0 there? The accelerations, good. Those are the slopes of velocity. And then it gave us the areas of the regions respectively were 8, 3, and 2. And I have yet to see them ever give you areas disrespectfully, like here are your freaking areas, students. So they usually do it respectfully. Okay. Is that what that means? I don't know. Okay. Oh, and then it says at t equals 0, the particle is at x equals -2. So if you've forgotten, we were using the x-axis as kind of a little track system for this particle to be moving in. So it's going left, it's going right, it's going left, it's going right. And when the velocity is positive, he's moving to the right. And when the velocity is negative, he's moving to the left. So he's starting off right there at -2. Okay, let's go ahead and answer the questions. Part A, on the interval from 0 to 6, which if you look is pretty much the entire graph, find both the time and the position on the x-axis when the particle was farthest to the left. And then it says to justify your answer. So anytime you read something and it's the superlative case, biggest, fastest, ugliest, farthest left, farthest right, that's optimization. But it's the easy optimization. It's not the optimization like write 2 equations and then see where the volume is a maximum. These are going to end up being EVT questions, which is the extreme value theorem. So first of all, if we're trying to figure out where the particle is farthest to the left, are we trying to maximize or minimize something? Remember, here's the x-axis. Minimize, good. We're trying to minimize its position. If it said farthest right, that's where the bigger numbers are found. That would be maximizing position. So that's farthest right. So where can, on the EVT, which is extreme value theorem, remember, where can the absolute, in this case, minimum occur? At one of 2 different places, either at endpoints, which are 0 and 6, or critical values. So let's go ahead and just set up what we know. When it's moving on the x-axis, you can let the position function be x of t. Okay? The velocity function is v of t. In fact, I would probably even write position equals x of t. So now you can refer to it as x. You've defined it once, now you can use it. So that helps with the notation. So we need to know then, what is the position at 0, and then what is the position at 6, and then what is the position at every critical value in between 0 and 6. So I left some space there. All right, so let's go ahead and find critical values of position. So in part A, we get critical values, remember, where the derivative is equal to one of 2 things. What or what? 0 or dne. Good. So I want to know where x prime of t equals 0 or x prime of t equals dne. And remember, the dne one is the one that most students forget to even consider. But y'all are not most students. Okay, so what's another name for x prime? V of t. So let's go ahead and write that as v of t equals 0. Or v of t equals dne. And again, this is the actual work that I'm showing in that little space for this problem. Well, I have the graph of velocity. So where is it equal to 0? It actually said in the description it's equal to 0 at 0, 3, and 5. So 0, 3, and 5. So underneath there I'll put t equals 0, 3, and 5. So by listing them in this fashion, I am essentially declaring them critical values. Now, is this graph ever undefined on the interval from 0 to 6? Does it have any holes, jumps, or VAs? No. So this piece here gives you no solutions. But at least we considered it. All right, so now we need to figure out where's the position at each of the critical values. But notice 0 is already taken into consideration, right? Because he's also a left endpoint. So we really just need to figure out what is the position at 3 and what is the position at 5. So this right here is not only collecting evidence to answer the question, this ends up being your justification. All right? So let's go ahead and answer that question. I'm going to bring this down here so I have room to do the other stuff. All right, what is x of 0? These are positions. Where is it at 0? It says right there in the question that at 0, it's at -2. All right, so I don't have to do much work for that. I just write it down. Now, remember what we said way up here. The position, where you are at any given time, is a function of your starting position plus your what? What do we call the integral velocity? The net change in position, the displacement. Yeah. So for each of these, I'm going to have to use that -2 as my starting position, because that's where I start at t equals 0. Remember, starting position also doesn't even have to correspond with 0. It could just be any point that we have, but it happens to be 0. So let's go ahead and do it in order from left to right. So what would be its position at 3? Well, it started at -2, and then what did it do from 0 to 3? Did it move left or right 8 units? It went left 8 units. So would I add or subtract the 8? Subtract. So -8 minus 2 is -10. It's that easy. The integral is the area, and the area tells you the direction traveled in that distance. Left or below means negative. All right, so then I know at 5, I want to know where it is at 5. So now I just show it again, -2 minus 8. And then what do I do with the 3? From 3 to 5, I'm moving back to the right, so do I add or subtract the 3? I add it back. So that ends up being -10 plus 3, which is -7. And then for 6, I got to do everything I did before. So -2 minus 8 plus 3. And then that last little piece from 5 to 6, I'm back going to the left 2 units, so I will subtract it. So -7 minus 2 is -9. Okay, so that's one way to do it. Now here's another way to do it. You could say it's -2 and then -2 minus 8. But on this one here, if you wanted to say it's -10 plus 3, and on this one you could say it's -7 minus 2, what am I essentially doing? Instead of adding everything up again, I'm just taking the previous answer and just adding the new part to it. That works as well. You're kind of accruing it, and that's enough to indicate your method. But it always works to show everything from the beginning. So now, by the EVT, oh, that's not a good color. I kind of obscure it. Let's use white. No, that doesn't work enough. Yellow. There we go. -2, -10, -7, -9. One of these is the maximum. One of these is the minimum. We want to know where it's farthest left, so that's the smallest one, which is what? -10. Now remember, we answer the question. Did it want the time or the actual position or both? Both, okay. So now you don't have to justify. You just say, so the particle is farthest left at t equals 3. Are there any units there, like seconds or hours? It looks like this entire problem is unitless, okay? So that's cool. And then you could say at this time, it is at x equals -10. So I don't know. Can anyone think of a better way to answer both of those in one sentence? The particle is farthest left at x equals -10 at t equals 3, or the particle is farthest left. What's that? I don't know. 2 sentences is enough. I don't know if you can combine those nicely into one sentence, but 2 sentences is fine. Okay? Did we need to do anything else for part A? We answered the question, and again, the justification is your computation of the positions at all of the values. So we got it. Now, this is going to pay off here. Knowing the story of the particle is going to help you in answering the rest of the question. So let's real quickly just go through the life of the particle. It starts at -2, and then we know that it moves left 8 units to -10, and then it moves right 3 units to -7, and then it moves left 2 units to -9. Okay? And we know that when it's moving left and moving right, it's doing so monotonically. Part B. For how many values of t then? Not for what values, but for how many of them on 0 to 6 is the particle at -8. Explain your reasoning. So he only has to be there for the briefest of moments, okay? In other words, how many times did it pass through the value of -8? Let's count them. It started at -2, right? And then we know it moved left. It went from -2 to -10. Did it pass through -8? Yeah, once, twice, or how many times? Just once, because we know on that interval it's moving left the whole time. All right, so then from -10, it went back to the right to -7. Did we pass through -8 again? Yep, so that was the second time. And then from -7 to -9, did we pass through -8 again? Yep. And so for part B, we could just say 3 times. And that's going to earn a check. Did it say to explain why or justify? It said to explain your reasoning. So if it ever says to explain rather than justify, that means feel free to use words, okay? You can actually describe how you came up with that. It could be pretty lengthy, right? The qualifications on this one is you had to discuss movement. You had to discuss motion. Okay? This is actually a what theorem? What VT? Not MVT. If I know that on one side I'm at -2 and on the other side I'm at -10, and I'm trying to prove that I was at an actual value on that interval, that's the IVT. This is actually an IVT question, but you don't actually have to use the name IVT. You could justify it or explain it some other way. The qualifications were, though, you had to discuss motion. So if you simply said, at 0, the particle was at -2, and at 3, the particle was at -10, therefore it was at -8 once, that doesn't work. So here's what you had to say. Something about the particle went from x equals -2 to x equals -10 for the first time. Then from x equals -10 to x equals, what was it, -7 for the second time. Then from -7 to x equals -8 for the third, and you might want to add this, and final, but you don't have to actually say that. It's just kind of nice, and final time. And I know my handwriting's horrendous, but there you go. So the key words here that describe movement are the whats? From, to, from, to, from, to. There you go. That was enough to get full credit for the explanation. There are other ways to do it that are actually more lengthy. You could say the velocity function is a continuous function, and the particle went from -2 to -10 monotonically. Therefore, by the IVT, blah, 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 it had to equal -8 at least once on the interval, or just once on the interval, and then do that for every interval. So it could get pretty lengthy. Now, the explanation is only worth 1 check. So if you don't get all 9 because for some reason you didn't talk about movement, you talked about stationary positions, you get 8 out of 9 instead of 9 out of 9. It's no big deal, okay? But just knowing that it's 3, you get the check for that. All right, any comments or questions then on part B? All right, part C. On the interval from 2 to 3, okay, so now at a little part of the interval from 2 to 3, that's going to be from here to here, from 2 to 3. Is the speed of the particle increasing or decreasing? Give a reason for your answer. This is review, right? The velocity for sure is increasing, right? Because the graph of velocity is going up. The slopes are positive. But remember, for speed, which is a scalar quantity, we have to check 2 things. Namely what? For speed, we have to compare the velocity to the acceleration. If they're the same sign, both positive or both negative, they're working together, and speed should be what? Increasing. It's like running again with a tailwind. But if the velocity and the acceleration are opposite signs, it's like running into a headwind. The speed is going to be decreasing. So let's go ahead and see. On the interval from, you can list it like this, 2 to 3, or you could do it with the compound inequality like they gave you. We'll say V of t is what? the graph of v of t is what? Positive or negative? Negative. And is it increasing or decreasing? Well, is this graph increasing or decreasing? Increasing. So you could say v of t is less than 0 and increasing. That's one way to do it. Or you could say on that interval v of t is less than 0 and v prime of t is greater than 0. You don't just want to say a of t here. Why? You haven't defined it, right? We're going to be looking around for a of t and it's not defined. But when you say v prime of t, now we know you're talking about the slopes of the graph. Okay? So as it is, because the y values are negative and the slope is positive, they're opposite signs. And you have to say exactly what the signs are. So either one of these would work. So speed is whatting? Decreasing. Yeah. Now remember, there was an easier way to tell, and believe it or not, the justification would still work, but I'm not a big fan of it. Anytime your velocity graph is moving towards the t-axis, whether it's approaching the t-axis from below, like it is from 2 to 3, or from above, like 4 to 5, your velocities are approaching 0 and the speed is decreasing. And if your velocity graph is moving away from the t-axis, like from 0 to 1, or from 3 to 4, or from 5 to 6, your speed is increasing. But you don't really want to justify it like that. It does work, but it's better to talk about the two things separately. Okay? So it's kind of interesting that the velocity is increasing, but the speed is decreasing because it's becoming less negative. The velocity is. All right, part D. During what time intervals, if any, that's mathematical foreshadowing. It means there might be how many intervals? Multiple or possibly none. Is the acceleration negative? Justify. Oh, I was worried. Usually these free response kind of end with something that's very thought-provoking. It requires you to think extra hard. This ended up with an easy one, right? To determine where the accelerations are negative, we want to know where the what's of this graph are negative. Slopes, right? So let's go ahead and hit the nail on the head. How about V, or let's go ahead and say acceleration, answering their question. Acceleration is negative when v of t is decreasing. You can do it like that, or when v prime of t is less than 0. Either one of those work. Now, we talked about this back when we did particle motion previously. We're kind of justifying it before we answer it, which is fine, because now we're giving ourselves something definitive to look for. Acceleration is negative when either one of those two things happens. This is on the interval, and it's probably easier just to say t epsilon and give the intervals in interval notation. Okay, so I want to know where the graph is going downhill. So that's going to be from 0 to 1. So open parentheses, 0 to 1. Union, is it going downhill ever again? From 4 to 6. Yeah, so union 4 to 6. You can do it like that. Or you could say, here's the other way, 0 less than t less than 1. And in this case, you would say and 4 less than t less than 6. So I'm a big fan of interval notation because it's a little bit faster. And again, there's no units, so you don't have to worry about putting seconds or anything like that. And so that's it. That's the whole question. That's worth 9 points. Do you all have any comments or questions on that one? Ooh, that was a nice sound to finish off with. All right, first of all, let's look at the scoring guidelines, and then we'll look at these scoring statistics, how people actually fared. All right, so this was question number 4, so I have it pulled up. Part A was worth 3 points. Notice you got 1 point for identifying 3 as a candidate. Did we identify 3 as a candidate? Yeah, we identified it as a candidate actually twice. Right here, when you set it equals to 0 and it shows up, he's identified as a candidate. Or if he only showed up right here as x of 3, that's also a candidate point. Did you consider the integral from 0 to 6? Did we consider that? We sure did. When we did x of 6, we were considering the integral, which is the negative 8 plus 3 minus 2 added to the initial condition. So we got that check. And then the final check for this one is the conclusion, which we totally got. Okay, at negative 3. Oh, they did it in one sentence. Let's read. Therefore, the particle is farthest left at time t equals 3 when its position is x of 3 equals negative 10. Okay, that's great. Next part was also 3. Now look where you get the first check. Its positions at 3, 5, and 6. Did we ever find its position at 3, 5, and 6? We certainly did. We found its position at 3, 5, and 6, not on part B, but rather on part A. So we didn't know it at the time, but we were getting points for part B already on part A when we were helping ourselves answer part A. That's pretty cool. And then the description of motion. So there's what I was telling you, the description of motion. So if you didn't talk about moving from to, you didn't get the check. But the conclusion by itself was one check. So if you just said 3 times and walked away, you got the check. Okay, now they listed it a couple different ways. By the IVT, there are 3 values, blah, blah, blah. All right, the next one, the speed, is 1 check. And then the last one was worth 2 checks. One for the answer, it's negative on the intervals. And then the justification, since the velocity is decreasing on these intervals, or since v prime is less than 0. All right, so out of 9 points, of course, I'm going to just assume that y'all think that y'all would get all 9 of those. That's fine. We don't have to take a poll on that. But what do you think nationwide the average was out of 9? 4, 3? Okay, that's actually a pretty good guess. Here's 2008 question 4. The average student nationwide out of 9 points earned 2.6. Wah, 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 wah. Hey, when everyone else is doing that poorly and you're doing so much better, that's padding. That means you're getting padding for your 5. You can afford to slip up maybe once or twice and still easily get the 5. That's pretty low. That is really, really low. Okay. Any other comments before we move on to the next one? 2008, number 4. No calculator. All right, the next one I think you'll like. It is a calculator permitted one. So now we're back to the calculator. So I have my calculator here. I need to switch back to function mode. Okay. Now remember, you want to use your calculator judiciously as a tool. You don't just pick it up and put it in an alpha lock mode and start typing in the letters of the question and expect it to give you all the answers, right? Okay, so I graded this one as well. And this one was a little bit more exciting or entertaining than Karen with the C, because it involved a baby elephant at a zoo. Oh, baby elephant. Okay, so this was the second question on the test. Your first 2 are with the calculator. A zoo sponsored a 1-day contest to name a new baby elephant. Not the old baby elephant, but the new baby elephant. Zoo visitors deposited their entries. They could come up with a possible name, and they deposited their entries not in a regular box, but in a special box, okay, suitable for a new baby elephant. Between noon, which now corresponds with 0, and 8 p.m., which is t equals 8. Okay, so we're starting at noon, going to 8 p.m. So there's an 8-hour period in which they can deposit their entries. The number of entries in the box, t hours after noon, is modeled by a differentiable, and therefore what? Continuous function e from 0 to 8. Values of e of t in hundreds of entries. So this is the first thing that threw some people off. The units are not entries, but hundreds of entries at various times are shown in the table. So we have now a representation of a function not from a graph, but from a table of values. So let's make sense of it. At noon, at t equals 0, how many entries were in the box? 0, 100, right? Which makes sense, right? If there was anything in there, then the contest was rigged. Someone put something before it was time. At 2 p.m., there were how many entries in the box? 400, and then 1,300, 2,100, and at the end of the day, when they closed the special box, they had a total of how many entries total? 2,300, okay? The key is, do you want to work with hundreds of entries, like 0, 4, 13, or do you want to actually add zeros and work with entries? If they give you hundreds of entries, you're probably going to want to work with that unit, okay? So just keep that in mind. Good. Use the data in the table table to approximate, so squiggle alert, right? The rate in hundreds of entries per hour at which entries are being deposited at 6. Show the computations that lead to your answers. So we're trying to approximate an instantaneous rate of change. That is the derivative. We're trying to approximate e prime of 6. So we can't find the tangent line with a single point, so we have to do a secant line approximation with 2 points. So here's what you're going to say. E prime of 6, what comes next? Squiggles. And we've done this several times. Is 6 one of the data points in the table? No, it's not. So if it were, you would consider the values on either side. So 6 would fall between 5 and 7. So this is their way of forcing you to use those points. So you have to show your difference quotient. That's when it says show the calculations. Show your difference quotient. Is it going to be 7 minus 5 over 21 minus 13? No, it's change in y over change in x. So it's 21 minus 13 all over 7 minus 5. That's your 2-for-1 answer. It's a difference quotient, so it indicates your method, and it's a numeric answer, so you don't even have to simplify it. But then what would your units be? Well, it's units of this divided by units of that, which is hundreds. Hundreds of what? Not hours. Hundreds of entries, and then per hour. Okay? Hundreds of entries per hour. So change in y over change in x. So you got to be careful when your tables are given. The x's are in the top and the y's are in the bottom. But for your difference quotient, you got to flip it. Y's in the top, x's in the bottom. All right. So I would do that on part A in the little space provided. I'm not going to even bother moving it down below. But that's all they asked us, right? All right. Any questions on part A? Do you simplify this? Only at your own peril, right? If you've locked in the point, and you think you've locked it in, but you go on and you mess up, you lose the point that you've already earned. So you're actually not locked in. I'm just going to leave it. Use a trapezoidal sum with 4 subintervals given by the table to approximate, so another squiggle alert, the value of this. And then using correct units, explain it. Okay, so right now you may be like, I have no idea what the 1 over 8 in front is. But I know that to approximate this, I need to approximate the integral, and then I'll multiply it by 1/8. So how do we approximate an integral? Well, using a trapezoidal sum with 4 subintervals. So from 0 to 8. So remember, we come up here to the data, and we calculate. From 0 to 2, the width is 2. From 2 to 5, the width is 3. Are we going to be able to use an equal subinterval? No, but that's not a problem. So we'll just continue on with the widths. From 5 to 7 is 2 again. And 7 to 8 is 1. Now, I think I will take this out of the way and paste it down below where A would be, because I want to be able to see my data points. So again, normally you're not going to get tunnel vision. You're going to be able to move your eyeballs up and down. So here's what you're going to say. You're going to say then, I'll start way over here, 1/8, the integral from 0 to 8 of E of t dt is approximated by. Now the 1/8, I'm just going to carry it through. It's 1/8. And now I'm going to move on to my trapezoidal rule. What number for sure is always part of the trapezoidal approximation? 1/2. Good. So we can still pull the 1/2 out front. Delta x, we can't pull out. So we're not going to be able to just add up all the y values, remember, and double the ones on the interior. You can only do that if they're equal subintervals. So what we're going to do is we're going to take the first width of 2, and we're going to multiply it by the sum of the 2 values on either side. So 2, the width, times 0 plus 4, plus the next width of 3 times the 2 y values flanking it, 4 plus 13. 3 times 4 plus 13, plus the next width of 2 times the 2 y values flanking it, which are 13 and 21, so 13 plus 21. And then the last width of 1 times the 2 values, 21 plus 23. Close it, and we're done. Okay, so notice you're still using each of the interior values twice. There's your 4 twice, there's your 13 twice, there's your 21 twice, but it's associated with different widths. Do you want to simplify that? You have your calculator. You want to type it in? No. This, again, is a 2-for-1 deal. You are indicating your trapezoidal method by the way you have it written, and it's a numeric answer. So you can stop. Yes, awesome. Now, to think about what the units would be, that's what the next question is. It says, using correct units, explain its meaning in terms of the number of entries. So let's think about what the units of the integral are going to be first. When I take units of E of t, which are hundreds of entries, and I multiply it by dt, that's times hour. If I just looked at the integral, it's going to be that aggregate unit, 100 of entries times hours. So what does the 1/8 in front? Well, what's our width from 0 to 8? Isn't it 8 units? So multiplying by 1/8, isn't that the same as dividing by 8? And what do we get when we have an integral divided by the width? Average value, yes. So this is an average value. So they're not going to give it to you as the integral over width. They're going to give it to you as 1 over the width times the integral. So whenever you see that number in front of an integral, 1 over number, it's going to be the average value of your integrand. The average value of the integrand. Integrand. So let's carefully think of what E is. E is, it tells us, right? E is what? E is the number of entries in the box t hours after noon. So I'm going to answer it down here where I have room. This, and again, I can use the word this because I'm only referring to the one thing they ask in this section. This gives the average, we're just going to throw that word in there, and then I'm going to come back and use their words. It's the average number of entries in the box, average number of entries in the box. And then what are the units? We need to put units in hundreds of entries. Good, in hundreds of entries. We talked yesterday about how some people forget to put the dependent variable in hundreds of entries from, and then we just list the time, from t equals 0 hours to t equals 8 hours. So again, that would be the engineering way to answer it. You could say over the 8-hour period from noon to 8 p.m. You could do that as well. But in general, this always works. So don't try and get too cute. It's the average value of whatever your integrand is. So when they define what E of t is, just reuse their words. The average number of entries in the box in hundreds of entries from 0 to 8. Okay? So let me go ahead and grab the last or the rest of this and cut it and paste it down here. So how could they have asked that a little bit differently? Well, instead of a trapezoidal approximation, they could have asked you for a left Riemann or a right Riemann. So the left Riemann would have been 2 times 0 plus 3 times 4 plus 2 times 13 plus 1 times 21. The right Riemann would have been 2 times 4, 3 times 13, 2 times 21, 1 times 23. And, of course, all that times an 8. Okay? So those are the 3 ways that they're probably going to ask you. If they did ask you for a midpoint, then you would have to skip intervals from 0 to 5. And 2 is not halfway between 0 and 5, so that didn't work. Okay. That's it. So, again, without looking now, if you ever see an integral with 1 over a number in front, it's going to be the what? The average value of whatever your integrand is. Okay? The average value. 1 over a number is the average value. That's a recent trend. They've been doing that a lot lately. Okay, part C. At 8 p.m., which is when they closed the special box, we had 2,300 entries there. At 8 p.m., volunteers began to process the entries. They processed the entries at a rate modeled by the function P of t. So now P of t is a rate equation, okay? It's modeled in hundreds of entries per hour. So whenever you're given a rate equation, immediately tell yourself, okay, if I integrate this, I'm going to end up with units of what? Just get rid of one of the pers. Hundreds of entries per hour times hours is hundreds of entries. So if you integrate the rate equation, P of t, you're going to end up with the net change in the number of entries processed, which is the total number processed, from 8 to 12. So they're going from 8 p.m. to when? Well, not noon. Remember, it started at noon. Midnight. They're working from 8 to midnight. Volunteers. Wow. They must be giving them like free peanuts or something. According to the model, how many entries had not yet been processed by midnight? Okay, let's think about that. Entries not processed. Let's go ahead and label it. Entries not processed. You could say by midnight if you want, by midnight. It should equal. Well, what's the easiest way to figure out? You know how many they ended up with, right? At the end of the box opening thing? If you take the total number they started with, subtract from that the total number they processed, you'll be left with how many were left over, right? So let's go ahead and do that. How many did they end up with at the end of the collection period? 2,300, all right? So I'm going to leave that as 23. And I'm just going to make a note here, that's 100 of entries. From that, we subtract the number that they processed. What am I going to do with P of T, which is in hundreds of entries per hour, to get the number that they processed? What do I have to do with that? Do I evaluate that at 12? Do I integrate it from 8 to 12? Or do I take the derivative of that? Integrate. Anytime you have a rate equation and you integrate it, you're going to get rid of one of the pers on the unit. So you end up with hundreds of entries. So we're going to integrate from 8 to 12 the P of T function with respect to T. And that's all you have to show for your setup. Now notice that this again, if you want to look at the units, this is hundreds of entries per hour times dt, which is hours. This whole thing gives you hundreds of entries. All right, so I'm keeping it as 23 minus the integral. And because the function was P of T, I can leave it like that. Now we'll go to the calculator. Let's go ahead and do this. P of T is kind of a long, ugly equation. I don't want to have to type it in more than once. So because it's a free response, let's go to Y1 and type it in there one time very carefully and make sure it's correct. So x cubed, click to the right, minus 30x squared plus 298x minus 976. So one time only, you double check, triple check, make sure it's in there perfectly. It looks good. All right, so now we'll go to the home screen, and we're going to type in exactly what we wrote on our paper. 23 total at the end of the night minus the integral, which is what? Bless you. How do we get the integral? Math 9. Good, math 9 from 8 to 12. And now, since I typed it in Y1, I can recall it, which remember is alpha trace. All of those green buttons at the top are unlocked. So if you forget where it is, you can actually search for it. All right, you have these little tabs down here. So we put it in Y1, and it's with respect to X. 7. All right, so let's go back to our paper, and I'll write 7, and what are the units? Hundreds of entries. And that's your answer. Now, here's where some students got messed up. They did the following. They went ahead and said it was 23, and they added 100 to it, and then they subtracted the integral from 8 to 12, and now you're left with this, 2,284. Is that a reasonable answer? You only had, what, 2,300 entries to start with? And you had volunteers working for 4 hours, and at the end of the night, there's 2,284 left? Those are worthless volunteers, right? They weren't working very hard. So to end up with 700 left, well, maybe you should have paid them or whatever, but 7 is more of a reasonable answer, okay? All right, so that takes care of, do we have to do anything else on Part C? Let's make sure. Nope, that was it. Now the last part, Part D. It's always the part where they make you go, according to the model from Part C, at what time were the entries being processed most quickly? When were the entries being processed most quickly? Is that optimization? Is that a superlative case? Yes, most quickly. So are we trying to maximize or minimize, first of all? Maximize. We're trying to maximize what equation? What is the equation that tells us how fast they're processing? P of t. We're trying to maximize P of t. Okay? So where do absolute maximums occur? At either endpoints or critical values. So what we're going to need to do again is we need to find P of 0. I'm going to jump down here. We need to figure out P of 0. When did they start? 8. They started at 8. And then midnight corresponded to what? 12. So I need to figure out P of 8 and P of 12. And then also P of any critical value. So let's do this. I need to figure out where P prime is equal to 0 or D and E. Now, here's where you have a choice. P of t is a cubic polynomial. So it's continuous and differentiable everywhere. So its derivative is never going to be undefined. You need to graph the derivative of P of t. Do you want to take the derivative by hand and type in that equation? Or do you want to let the calculator graph the derivative for you, which it can do? Yeah, you have to make that decision. Now, this one is a pretty easy one to do. So P prime of t is equal to 3t squared minus 60t plus 298. You don't actually need to show what the derivative of that equation is because it's not actually required. So I'm just going to show you the other way to do it. You could certainly do that and then set it equal to 0. You're going to get a check for setting it equal to 0. And now you have two options. You can either graph this in y2. You don't want to get rid of it from y1 because you need to go back to that to evaluate it. So just turn it off. You could turn off an equation by clicking on the equal sign, and now it's not highlighted. Now you could go down here to y2 and either type in 3t squared minus 60t, blah, blah, blah. Or if you remember, there's a way to have the calculator take the derivative for you. From y2, you hit math 8, which is the derivative. You take the derivative with respect to x of what is in y1. So that's alpha trace number 1. Now the key here is not to put at x equals 5 or at x equals 7, but to do it for all x, if you remember doing that. And without giving you the equation, it's going to take the derivative of this in here. Now because we want to know where it's equal to 0, here's what we want to do also. You want to sketch 0 somewhere else, in some other y value. When you solve an equation, set it equal to 0. And now set your window. We're looking up from the window 8 to 12. And now because we want to know where it crosses the x-axis, negative 10 to 10 is not bad, but I always stretch it out. Negative 3 to 3 stretches out your graph, and it keeps the x-axis right in the middle. And now you're looking for points of intersection. How many do we have? 2. Now this one is the location of a local max or min. If the derivative goes from positive to negative, that's a local max when it goes from positive to negative. And this one goes from negative to positive, so that's a local min. But for the EBT, we need both of them. So here we go, very quickly. Second trace, number 5, enter, enter, scroll to the left, and hit enter. Write it down underneath your P of t equals 0. So you get t equals 9.183. Now here's what we're going to do. Once we write it down, we're going to put equals A. And you're going to go to your home screen now, second quit, and you're going to hit X stow as alpha A. So now you've got that value locked in as alpha A. One more time, go to the graph, second trace, number 5, enter, enter. This time, scroll closer to this one here and hit enter. And now we write that one down, t equals 10.816, and we're going to store that as B. So if you go to the home screen now, hit X, stow, alpha B. And now we have both of them locked in. Those are your two critical values. So I wrote it as A and B on my paper after I wrote down the 3 decimals. Now all I got to do is come back over here and put P of A and P of B. Now this is why we didn't want to get rid of the derivative from part 1 or in Y1. We can evaluate that now very easily from the home screen. Alpha trace number 1. That's the P function still, remember? So if I open parentheses and type in an 8, that'll give me the processing. 0. Well, that makes sense. They just sat down. They're just walking in. They're not doing anything. Recall it or type it in again, y1 now of alpha A, and you get 5.088 hundreds of entries per hour. Recall it, come back in here, replace that with alpha B, 2.911 hundreds of entries per hour. I'm writing these down. And then the last one, recall it and just come back here and type in a 12, and you get 8 hundreds of entries per hour. And now with all the data there, we answer the question. It says, at what time? So, what's the answer? So, processed fastest when? Yeah, we'll just say at T equals 12 hours, which is at midnight, which kind of makes sense if you think about it, right? They're volunteers. They're like, oh, crap, we have to leave at midnight. Crap, there's still how many that we have in process? 700. We better get going, you know? And it's also the energy of anticipation. It's what you feel right now when it's almost over and you're about to get out of here and go on to the next thing, okay? So that's worth 9 points. On the scoring guidelines, we didn't get a chance to look at it. But real quickly, the scoring statistics, if you want to look at it. This was question number 5. The average score, look at it, 1.75 the average student got out of 9. If you're getting 3 or 4, or heaven forbid 5, whoa, you're launching yourself into the upper echelon. If you're getting all 9, you're a math god. All right. Y'all may leave 10 seconds early. Have a great day.